An object speeding up around the circle feels two different pulls at once. One pushes it forward along its path, the other yanks it straight toward the center. Both fall out of a single derivative. Take the velocity, apply the product rule, and the acceleration splits cleanly into a tangential piece and a radial piece. When we describe motion in polar coordinates, the acceleration vector has two components, a radial component, a sub r, along the r-hat direction, and a tangential component, a sub theta, along the theta-hat direction. We write the acceleration as a sub r times r-hat plus a sub theta times theta-hat. Here is the subtlety that makes this whole derivation interesting. As the object moves around the circle, the unit vectors r-hat and theta-hat themselves swing around. They point in new directions at every instant, so unlike the fixed Cartesian axis, they are not constant in time. Let's compute the tangential component first. Recall that in polar coordinates, the velocity of a particle on a circle of radius r points purely along theta-hat. The velocity equals r times d theta dt times theta-hat. Now suppose a tangential force is speeding the particle up, so d theta dt is changing in time. To get the acceleration, we differentiate the velocity with respect to time. Because the velocity is a product of the scalar speed and the unit vector theta-hat, and both depend on time, we must use the product rule. This gives two terms. The first, r times the second derivative of theta, d2 theta dt squared, times theta-hat comes from differentiating the speed. The second, r times d theta dt, times the time derivative of theta-hat, comes from differentiating the unit vector. Now we handle that second term, the time derivative of theta-hat. In Cartesian components, theta-hat equals minus sine theta times I-hat plus cosine theta times J-hat. Differentiated with respect to time using the chain rule because theta depends on time. The derivative of minus sine theta is minus cosine theta times d theta dt. And the derivative of cosine theta is minus sine theta times d theta dt, pulling out a common factor of d theta dt. The bracket becomes minus cosine theta times I-hat minus sine theta times J-hat. But cosine theta times I-hat plus sine theta times J-hat is exactly R-hat. So the time derivative of theta-hat equals minus d theta dt times R-hat. It points along minus R-hat. Substitute that back into the acceleration. The first term stays r times the second derivative of theta times theta-hat. The second term becomes r times d theta dt times d theta dt along minus r-hat, which is minus r times the quantity d theta dt squared times r-hat. So the full acceleration is r times the second derivative of theta times theta-hat minus r times d theta dt squared times r-hat. Reading off the components, the tangential component a sub theta equals r times the second derivative of theta with respect to time. Writing omega for the angular velocity d theta dt. The radial component a sub r equals minus r times omega squared. Look closely at the radial component. It equals minus r times omega squared. Radius r is positive and omega squared is a square, so it is never negative. The minus sign in front therefore makes a sub r negative no matter which way the particle circulates. A negative radial component means the acceleration points opposite to r-hat, and r-hat points outward. So the radial acceleration always points inward toward the center of the circle. That inward pull is the centripetal acceleration, and it is present whenever the object moves along a curve. Let's put these formulas to work. A particle moves in a circle of radius r. At time 0, it sits on the x-axis, and the angle it makes with the positive x-axis grows as theta of t equals at cubed minus bt, where a and b are positive constants. We want the velocity vector, the acceleration vector, and the time at which the centripetal acceleration vanishes. Start with the derivatives of the angle. Differentiating at cubed minus bt once gives d theta dt equals 3at squared minus b. Differentiating again gives the second derivative 6at. Now build the velocity. The velocity is r times d theta dt along theta hat. So it equals r times the quantity 3at squared minus b all times theta hat. That is part A. For the acceleration, use the two components we just derived. The tangential component is r times the second derivative of theta, which is r times 6at, or 6art along theta hat. The radial component is minus r times d theta dt squared, which is minus r times the quantities 3at squared minus b squared along r hat. Putting them together, the acceleration equals 6art times theta hat minus r times the quantity 3at squared minus b squared times r hat. That is part B, the full acceleration in polar coordinates. Finally, when is the centripetal acceleration 0? The centripetal or radial acceleration is that minus r times d theta dt squared term. R is not 0 and the square is 0 only when the thing being squared is 0. So we need 3at squared minus b to equal 0. Solve for t. Move b to the other side to get 3at squared equals b. Divide by 3a to get t squared equals b over 3a. Take the positive square root, since time is positive and the centripetal acceleration vanishes at t1 equals the square root of b over 3a. Here is the physical picture at that instant. The quantity 3at squared minus b is exactly d theta dt, the angular velocity omega. So at this moment, omega is momentarily 0. The particle has slowed its rotation to a stop, reverses, and begins circulating the other way. With no angular velocity, there is nothing to pull the particle inward, so the centripetal acceleration is 0 right then. Notice the tangential acceleration 6art is not 0 there. The particle is still angularly accelerating even as its instantaneous angular speed passes through 0. Step back and see what one derivative gave us. Differentiating the velocity with the product rule, split the acceleration into two physically distinct pieces. The tangential component, r times the second derivative of theta, is non-zero only when the speed is changing and it points along the path. The radial component, minus r times omega squared, is always negative, so it always points toward the center. Every curving motion carries this inward centripetal acceleration, the signature of turning, hiding inside a single time derivative of the velocity. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.